Morning, good afternoon, and good evening. My name is Eric Du from University of Florida. So today is my great pleasure to introduce our project, Cognition-Driven Wayfinding System for Search and Rescue Augmented Reality Applications. In this project, we hope to develop the future AR technologies for the search and rescue activities. This is a collaborative effort among University of Florida, Virginia Tech, TICS, and Northeastern University. The project is funded by PSAP AR and the PSAP UI UX programs. This is the overview of my talk today. So first, I'm going to share the thoughts we have about the challenges of augmented reality for search and rescue. AR is a perfect technology, but it's not yet the perfect tool for search and rescue activities. Then I'm going to cover the two phases of our research. The first phase, we developed a cognition-driven wayfinding system that can dynamically adjust the user interface based on the real-time measure of the cognitive load of a firefighter. And then I'm going to talk about the ongoing phase 2, which is our AR design, especially the cognitively optimized AR design for supporting the search and rescue. And also, by the end, I'm going to cover our future plan. Building environments such as buildings, underground utilities, bridges, roads, they are becoming more and more complex nowadays. I'm not just talking about the complex floor plans, but I'm also talking about the systems such as mechanical systems, electrical systems that are used in modern buildings. And also the designs of model buildings are become so flexible, so we are talking about lots of open areas and confined spaces are mixing up. And also inside modern buildings, we are using so many signage systems. Everything can pose significant challenge to search and rescue activities such as visual distraction. So maybe the problem is not we don't have enough information, but it's we have too much information to digest in search and rescue. In fact, disorientation is a major cause of injuries and fatalities for firefighters. According to NFPA, failure of the emergency response team to conduct timely and accurate assessments on the affected environment is a major contributor of casualty and property destruction. About 43% of firefighters' injuries were related to disorientation. And there's a significant challenge with the retreat, which means it's easier for them to find a way in, but it can be difficult for them to find a way out. Talking about the technologies to support search and rescue, more and more people are thinking about augmented reality. AR is a highly visual interactive method for presenting relevant and useful digital information in the context of a physical environment. Putting on a VR goggle, you see the real world, you also see the computer-generated information. So it's a perfect tool to support operations, including search and rescue. And we have seen so many opportunities with AR for search and rescue, such as the enhanced navigation, enable this better offsite on-site team communication, and also it can increase situational awareness of first responders, such as showing the hazard warning. But meanwhile, we have to admit, augmented reality is still an immature technology, and in terms of the scanning, environmental understanding, the visual effects and everything. And also, we don't quite know yet the impacts of AR technology on the cognitive functions of first responders. Talking about the challenges of AR for search and rescue, there are so many. In this talk, I just want to cover 3 of them. First, AR is different. So the user interface and the user experience with augmented reality is so different from regular head-side display or any other kind of handheld displays. There are so many options with AR, but we don't know what options, what functions are the best for search and rescue. Second, in augmented reality, you can look through the lens and see the real world. But that means your AR can be easily affected by different light conditions. If you're moving from indoor to outdoor or the vice versa, you will see a significant challenge to see things clearly. And last, augmented reality is based on something called environmental understanding, which means your AR goggle will need to scan the environment, build a 3D model. So it needs to understand the surrounding first before it knows where to anchor, where to put this computer-generated objects or information panel to. Unfortunately, the scan can be easily affected by your moving speed, and also there's an upper limit for the memory, which means your AR headset can only remember this much space. It is a challenge for large-scale search and rescue. This is a video people always use to show the potential of augmented reality, but I think this one also shows the challenge of that, which is information overload. In augmented reality, you can anchor computer-generated objects to the real world, to the surface of the real world. You can anchor everything to the body of your own body and others. And also, you can show the permanent information in your view. It means that you have so many choices, but it also generates a potential risk of information overload. We have to make a selection. We have to decide what functions, what UI are the most suitable for search and rescue. Second, like I mentioned earlier, because in AR you can look through the lens, you can see the real world, it also means that your AR headset can be easily affected by the external light condition. For example, in this case, when I was indoor, the 3D object in the view was sharp and clear, great effects. But when we moved outside, and it was a sunny day outside, it was barely visible. It was very difficult for me to see the boundary of the 3D object like here. And also, this video showed that I was moving from indoor to outdoor. So my eyes were adjusted to this indoor view. And once I can see that I moved outside, then all of a sudden, I couldn't see the 3D objects. One thing because of the light condition, it's become so lighter. And also, it was because of the strong reflection from the inside of my lens. It made everything so fuzzy. And last is also about the environment understanding. Like I mentioned earlier, AR totally depends on how much space it sees and memorizes. But unfortunately, there's a limit for that. Scan result of the stress testing of HoloLens 2. We used the HoloLens 2 to scan a building on UF campus. As you can see, this is the hallway and this is the stairway. We found two problems with augmented reality for search and rescue. The first problem is if a person runs very fast, then the person is going to miss a lot of data points, such as the holes you see here. Unfortunately, in search and rescue, first responders are usually moving very fast. That means significant pressure to the HoloLens scan. And the second problem is there's upper limit for the memory. As you can see, when our researcher moved from this end of the hallway and to the stairway, HoloLens start to cut models from this end because the entire model reaches about 35 megabit. That means there's a limit for the scale you can apply augmented reality in search and rescue. So because of that, for example, if you place the label here to show the hazards in this room, after that, if you move to all the other end of the hallway, then when you come back here, your place the label was gone. That means the current AR, the current HoloLens headset can be a problem for large-scale search and rescue. So many potential solutions to improve the current AR technologies from the hardware perspective, from the software perspective. And our answer is cognition. We believe the three problems we identified, the UI selection, the impacts of indoor and outdoor light conditions on the view, and also the size of the search, that can all be somehow resolved with a cognition-driven augmented reality. So our goal is to explore and design a cognition-driven adaptive AR system for search and rescue. And the hypothesis is if we can adjust the AR UI and the AR function based on the real-time measure of cognitive functions of first responders, then we can somehow overcome the present technical limitations without or before the substantial improvement of AR hardware technology. So to achieve this goal, we need to do two things. First is to develop an automated UI adjustment method based on the prediction of real-time cognitive load, and we call this Cog-DNA system. And based on that, we will develop this future AR system, which we call SearchAR, that are driven by each first responder's unique cognitive features measured by Cog-DNA. And by doing that, we hope the system is smart enough to present the right amount of a user interface, the correct UI depending on if you're indoor or outdoor, and also adjust correctly, intelligently adjust the environmental model based on your cognitive need. Now let's talk about phase 1, Cog-DNA, Cognition-Driven UI Adjustment Method. The idea is if we can measure a person's real-time cognitive load and predict the person's next moment load, so maybe we can adjust what information we should show and what information we shouldn't show on the display. It's either for augmented reality or virtual reality or any kinds of a head-side display. The first question is, what information is relevant? How does a person mentally model a space? And this is about spatial understanding and multimedia learning. Technically speaking, we use three kinds of information to understand the environment: landmarks, roads, and a survey. Landmark is something you memorize, such as a potential building, certain kind of plans inside the office room. The roads is actually you are connecting those landmarks, such as after 2-3 weeks, and you start to memorize, I need to go straight forward and turn left and then turn right so I can get my office. And the survey is the mental map. So once you are exposed to a place long enough, close your eyes and stand there. You can picture where the grocery store is, where the office building is to your current place. So we rely on the three things, and there are different ways to display the three things, such as the phonological or the verbal textual instruction, the visual, spatial, and haptic, or the mix ways of showing the information. So now, in this dimension, we have three types of spatial information, and in this dimension, we have different kinds of way to display the information. Then this becomes some kind of a matrix, and each person will have their preferred combination at a certain moment, and that can be different across time. So for example, literature shows that when you just enter into space, it's easier for you to rely on landmarks and plus textual information. But when you are tired, when you are exposed to this task long enough, then it will become more difficult for you to digest the textual landmark information, but maybe some visual display of the route information. So based on the understanding of how a person understands the environment and sense the environment, we designed our relevant UI for search and rescue. And this is a quick example. In this case, you see we do have some textual information, and we have different logo symbols to show the key landmarks and the hazard type. We also have this mini-map to show the relative orientation and location, which is really corresponding to the survey knowledge. And also we have different ways of showing the same type of information. For example, we could just be highlighting the symbol to show the hazards, or we could give you some verbal or textual information. And then we use different neurophysiological sensors to sense your cognitive status and predict your cognitive load. So when you are using different kind of UI, when you are using different types of wayfinding information, we measure the blood flow in your brain, we measure the pupillary size change, we also measure how you move inside the space. So based on all the three things, we can predict or tell what's going on. Are you tired or mentally fatigued? We also applied machine learning technologies to predict your next moment cognitive load. So this is a quick demo. If you go to this website, cogdna.com, and if we are running our experiments at the University of Florida, you will see this ongoing brain map, this ongoing, eye tracking attention patterns, and also the online prediction of the person's cognitive load level. Now imagine this, we give you different kind of wayfinding information, we see what's going on with your brain function. Now we build your personalized model of what you like, what you don't like, at what time point of a search and rescue task. So based on the developed Cog-DNA system to predict a person's cognitive load based on different kind of wayfinding UI, we performed a set of user studies since 2020. And at that time, the AR was not mature enough for us to run any user test. We adopted AR in VR test, which means we create this AR UI inside virtual reality and run our Cog-DNA system to test what's going on. So we recruited firefighters from Bryan Fire Department, Gainesville Fire Department, and Boston Fire Department, and then we ran experiments we observe their real-time brain functions here. The red color shows more oxygen consumption, the blue color shows more carbon dioxide, and this is their eye tracking trajectory and their pupillary size. And based on that, we adjust the wayfinding information based on the machine learning, and we see would that improve their search and rescue performance. And these are some very interesting findings. First, we did see certain forms of wayfinding information are more effective than others, but individual differences exist. Like I mentioned earlier, people are using landmarks, routes, and survey knowledge for their spatial understanding. So we compared them, and the control group means we didn't give them anything. So they needed to rely on free navigation to find the missing victims. As you can see here, looks like most people prefer to the route information, which means instead of giving them the maps of a building, just tell them the direction. Just go straight forward and turn left. That is the easiest way for them to find the direction. And we can also tell this from the NASA TLX subjective mental load evaluation. Looks like giving them the landmarks always increase the perceived mental load and decrease their performance. And also the route, represent a good amount of load, a relative, good level of load, and also the best performance. But meanwhile, please check all the black dots. Each dot represents a person. Now you do see, yes, in general, we see that overall trend, but each person is so different. For example, for this particular dot, that person, is definitely preferred to use landmark information than the route information. It means that, we don't have a one-size-fits-all solution for the future AR UI. We might need to build a personalized model for each firefighters, for each first responders. And we also tested if we put everything together, like changing the UI automatically driven by machine learning and the prediction of the person's cognitive load, would that work? And in this task, they were required to search 3 victims in a 4-story building. And as you can see that, this color shows the UI was on and it shows a higher cognitive load. And when we sense the higher cognitive load, the algorithm, the machine learning turned off, feed out certain UI, especially the textual information, and we did see an immediate drop of their cognitive load here. We also compared, using the traditional approach of showing everything and using our approach of cognitive load driven UI, what's going on. And this one shows, the examples of 6 firefighters. It did see that, it did show that with this automated adjustment, the cognitive load was reduced. Adaptive systems seem to be more welcomed because if you check, do you think the UI helps you during the wayfinding task? And lots of them voted yes, and lots of them say, I like the adaptive system driven by the cognitive load. It represents the lower lower effort. But meanwhile, some of them complained that I'm feeling more tired with the adaptive system, and most of them, claim that they felt their performance was worse using the cognitive load-driven method. But in fact, their performance was better. So we start to see this kind of a mismatch in their perception. Very interesting result. So by the end of phase 1, we understood how we should adjust the UI based on the cognitive load measures, and we applied this AR in VR approach. So now we are moving to phase 2. We wanted to move the findings to an AR environment, but we start to encounter problems immediately because we notice that AR UI is so different. So the first thing is the multimedia learning, the wayfinding, 3 types of wayfinding information. What are the realization of them in AR environment? What they look like in AR environment? So our first task is to perform user-centered design. We actually conducted a 6 months user-centered design effort. We engage subject matter experts across 3 different regions, Virginia Tech, Texas, and Colorado. And they represent varying expertise and experience in search and rescue, such as the program staff, chiefs, emergency service training personnel. So we performed a series of interviews followed by this user experience engineering approach, and we model their workflow, model their work roles, and also model their perceived obstacles and needs in search and rescue. So this is an example of our findings. In this case, we identified the key barriers. Number 1 is the lack of descriptive details of information received and sent about search and rescue. And the second is how to pinpoint locations of key personnel, the hazards, landmarks, etc. And also the lack of effective and quick communication with other ground personnel and command post. And this example showing that how we design the user experience. So user experience is different from user interface. You can imagine the user interface is the screenshot, is a snapshot of what you see, and the user experience is more about the flow of the change of UI, the flow of your functions. So in order to get a better understanding of what they need, we iteratively develop this conceptual design from the ecological, interaction, and emotional perspective. These are showing some sketch that we are using to communicate with the stakeholders, subject matters, experts. And we also developed the storyboard. The storyboard is used to envision the workflow in a certain search and rescue event. In this case, we imagined with our subject matters that how we look for missing people after earthquake hazard. And during this walkthrough of the workflow, we could better understand the functions needed, such as the area size marking, the hazard marking, communication, and also localization. And this one shows further the identified barriers and what we can do with augmented reality. And once again, from this process, we better learn how different kinds of wayfinding user interface, different kind of elements are coming together as a dynamic system, are flowing in a continuous task from the beginning to the end. So now it becomes more variable, becomes more vivid, so we can better understand how the UI is changing over time. And based on that, we have a better sense at how the cognitive load would be playing the role in changing the UI at different time points of a search and rescue task. And in order to engage our subject matter experts better during the pandemic, we actually use this online tool, Figma, that this is an interactive web browser type of tool. So we basically map we visualize the UI from AR, and we mark all the functions, and the subject matter experts, they can go to the website, they can use their mouse to mimic the way they are using their fingers to interact with the AR, and in this way they can provide their knowledge and their comments on what should be included, what shouldn't. So from this user engagement process, we now understand much better that what the unique UI for AR. And to resolve the problems of the environment understanding, like AR can only understand and scan this much of the space. In order to resolve that problem, we are developing this human-robot collaborative approach for search and rescue. So the idea is, if AR cannot scan that much with good quality, why don't we use a robot dog? So the robot dog can scan the environment, build a 3D model, and we push the model to the AR goggle, and all the spatial model is stored externally, by a robot dog, and is scanned by a LiDAR scanner instead of the AR. In that way, with this existing current AR technology, we can perform a much larger scale of search and rescue. And this one shows that we push the scan model from the robot dog to AR goggle, and we line up the view angle. We can even create this seeing through wall effects with HoloLens 2. So as you can see here, we're exploring all different options, all the crazy new UI functions with AR technology. It's still following, I have to say, still following the multimedia learning theory and spatial learning, the 3 types of wayfinding information, but it's just in much different format. And meanwhile, we are integrating the Cog-DNA system into the AR system. Like in this case, we measure the cognitive functions with neuroimaging, eye tracking, and we push that to augmented reality to see if everything worked in VR environment can also work in our AR system. What's next? So we're going to perform 2 field studies to examine our AR system. The first field test will be performed at the University of Florida and also Virginia Tech. So we build a one-to-one digital model of a building at the UF called a Versim Light building, and we design the AR UI with this virtual environment because it's easier for us to design that in our life, and then we moved everything with a real HoloLens 2 AR headset to the real building and test everything. So we're going to perform 5 search and rescue scenarios, including 3 indoor search and rescue tasks and 2 outdoor. We want to focus on the individual level experience with cognition-driven AR system, how that is affecting their cognitive load, how that is affecting their search and rescue activities. And the second field test will be performed by the end of next year. It's after our AR system design is done, and it's more for validation purpose. So we will be performing this realistic technical search and rescue at the disaster city, at the TICS, and we'll be focusing on the collaborative search and rescue with teams of 4 to 5 members. We believe the potential impacts are broad. First, from this project, we will discover transferable AR user interface and interaction design principles for the future search and rescue and potentially other emergency tasks. And we hope our cognition-driven methods can help overcome the present AR limitations, such as we don't know what UIs are best fitted at what time points. We don't know how the external light conditions will be a significant challenge in real-world applications, and also the size of the scan. So we hope by marrying the cognitive load, and we can present only the needed UI, we can present only the needed lighting and and brightness to the first responders. So without significantly changing the existing AR technology, we might still turn this AR into a variable solution for search on SQ. And of course, the field test we collected from field test 1 and field test 2 will be used to get adoption of multi-user AR in team-based search and rescue. Last, I really want to say thank you for all the public safety organizations that agreed and have participated in our experiment, our study, including TICS Disaster City, National Volunteer Fire Council, Texas A&M Task Force 1, Bryan Fire Department, Gainesville Fire Department, and the Virginia Tech Rescue Squad. And of course, to our wonderful research team, so we have a good combination of industrial and system engineering, human factors, building science, and also we have retired first responders on the team, so that we bring vast of useful knowledge from both the practice and also academia together to make a great system. These are the memorable moments that in the past several years we really enjoyed working with this wonderful team. Thank you, and if you have any question, please drop me an email.